So I'm going to solve for molality. Delta T equals IKM. I'm going to solve for that quantity right there. M equals delta T over IK. Delta T first. Well, it's 106.7 minus 100. So you would have to know the boiling point of water and the freezing point. Just take the difference. It says it's a non-volatile, non-ionic solute. What's that? It'd be 1. The only way, oh, that doesn't look like 1. The only way it's going to be anything besides 1 is if it's ionic. And this says it's not ionic, so we know it has to be 1. All right, K has to be the K for what molecule, anybody? For water. The solvent, and that's given, is 1.86 kilogram degrees C per mole. Okay, so you're going to do that multiplication. That's going to get you in units of moles per kilogram. You're almost there now. Okay, you're going to take this quantity, your answer. Now you do the conversions, just like I was talking about. So get rid of the kilograms. This is kilograms of what, anybody? Solvent, which is water. So you multiply by the 650 grams of water, change that to kilograms. Okay, now what? Oh, that's the answer. It's moles. This. Is that all right? If I could take one more step, say to get grams, if I need a mole mass, or whatever it asks. Okay, cool. Who's next? Yes, yes. Spring 10, second here, let me find that. 76, there we go, that's helpful. Okay, 20, this is on page 76. You're talking about the phosphate question. Is that right, this one? Okay. Okay, yeah, this one is definitely exciting. Did you want A or B or both? What are you looking for? Okay. Here, we have phosphate buffer, so that is Na2HPO4 and NaH2PO4. This is definitely a buffer. Why is that? Well, first of all, who cares about the phosphate, the sodium in the phosphate? One has one more H than another. They're a buffer pair. Now I'm going to write the numbers underneath. Get that all squared away. Let's see, this is 400 milliliters, 1.8 molar. This is 130 grams. Okay, this has a pH equal to, no, that's not a pH. Oh, resulting is then adjusted to the, oh, we don't know the pH. Then this, you get to this secret pH, whatever it is, by adding 6 molar NaOH. Okay? So they want this secret unknown pH. I'm sure they want us to find it. Yeah, there it is in part A. So part A, let's find the pH. Okay? Question makes sense? Okay. So it's a buffer, Henderson-Hasselbalch. Okay? So there's a couple things we need to figure out here. Let's start off with the base and the acid. Okay? So the base is the one, I'll ask you, which one's the base, left or right? How'd you know that? Besides guessing. It has less hydrogens. Okay? Alright, so for the base, I need to change this. Well, I have molarity already, so that's good. 400 milliliters, and did it give me the mass of the other one? Let's see. Let's just, let me change it to moles for now. Okay, so 1.8 molar times 400 milliliters. And I need to change to 400 liters, so I get in moles. Let's see. 1 liters, 1,000 milliliters. Okay, this will be moles of the base. Is that right? The reason I'm going to moles is because of the volume. I don't know how it's going to change when I add this one. It's safer to be in moles. Okay, now let's do the same for the acid. Acid, it's 130 grams. Now I need its molar mass. Let me see if it's here in the answer somewhere. 119.976, okay, whatever. All right, so this will be the moles of the acid. Okay, these numbers, this number is going to go here, and this number on the bottom is going to go there. Is that all right? Okay. So they'll just be numbers. You could calculate that if you want to. The next part is figure out what's Ka. All right. So let me write the reaction. And they give you in the question K1, K2, and K3 because this comes from phosphoric acid, H3PO4. Okay, what I'm going to do for this is write the general equation either for the acid or base, whichever one I feel like it. And you'll see why I do that in just a second. Okay? It doesn't really matter. I usually do it for the acid just because I like acids better usually. Everybody likes to take some acid. So let's do that. H2PO4 minus. So I got rid of the sodium because it's a spectator. I don't care about it. Write the general equation for it. You'll see why I'm doing this in just a moment. So the acid loses a proton, and the base gains a proton. Cool? Okay. This is Ka, what? 2 because I'm losing the second proton. Is that okay? Originally it was H3PO4. I lost now 2 protons. Ka2 is given in the question, 6.3 times 10 to the minus 8. Here's why I did this. When you write the general equation for an acid, you'll have the conjugates in there. And so this will, because I need to figure out what K is, and it's a polyprotic, I want to write the reaction because I'll know it'll help me recognize if it's 1, 2, or 3 by knowing which velocity the proton is. And it's usually easier to write the acid, general reaction for the acid, because polyprotics are, you have an acid, you're losing them. So it'll be more recognizable if you write the acid in the reactants. So that's the general rule of thumb. If I'm dealing with polyprotics, I'm always going to write the acid, the reactions down, usually for the acid if possible. Okay. So this helps me find this is Ka2. So then pKa2 is the negative log of Ka2. Is that okay? That's part A. This is pretty classic. You just Henderson-Hasselbalch this thing. All good? Yep. That's the easier part of the problem. Okay, the more fun part of the problem is next. Part B. Yeah.
So it doesn't really matter which KA we're going to use in that formula, whether we're going to use the first, second, and third one.
I mean, any K, it doesn't matter which K you use, it could be any possible K. Of course, only one of those Ks is the correct K to use. And it has to apply to the reaction of the buffer. So usually what I do, because Ka values are more normally tabulated, I will pick the acid and then write the general reaction for an acid. Of course, that includes both parts of the buffer, and that helps me figure out what the K is. Typically, we have something like HF and F minus, so you just look in the back for HFKA. But in the case where it's a little more messy like this, it's easiest to write the reaction. Okay? Okay, part B. In this part, determine the amount. So we want to add and make the pH equal to 7.4. What I want to know is how much I'm adding of this in the how much in milliliters am I adding of this thing? Okay, so how do you do this? This is also Henderson-Hasselhoff. Okay, I have a buffer, so I can always punt to Henderson-Hasselhoff. Let's write this out. Okay, this is the part we're going to mess with, so I'll leave it blank for now. Okay, pKa, that's from before, same. You haven't changed the buffer. pH, they just told you what that number is. So typically we're finding pH. Here we're being told. Okay. Now, I'm adding, let me write the buffer down one more time, different color. There's H2PO4 minus and HPO4 2 minus. There's the buffer one more time. Remember, I'm adding NaOH. Okay. NaOH will react with which side, right or left? Right or left? The left. How did you know that? That's the acid, yeah. So this is the acid, this is the base. So this one's in the base here will react with the acid. Okay? Okay. Now for the really exciting part. B and A from the previous part, same numbers, will go in here. But here's the problem. That base is going to react with the acid, so the acid will lose a certain unknown amount. And the base is going to generate more. I'll write that out just in case that doesn't make sense verbally. Then we'll come back to it. So that acid is going to react with this base. This is just a generic acid-base reaction now. The acid loses a proton. The base is going to gain a proton. Is that okay? So let's say I have, I don't know, A amount of this and B amount of that. Whatever. I don't know what this is. Okay? Usually in the previous question, we did HF earlier during the review. I told you it was like 0.2 of HCl I'm adding, or whatever it was. I don't know this one. That's what I want to find. So just call it X. Now, which one of these is going to be the smallest number? Which one of these three is the smallest number? X. Yeah, it's always going to be what you add to the buffer. Whatever that is. So I'm going to lose it back on that side and add it on this side. Is this too crazy? No, you're totally fine? Okay. So this is A minus X, 0, and B plus X. Okay, now I can go back to my equation. This is what I was trying to say verbally. So the base plus X, the acid minus X. Remember, A and B are from part A. Those are numbers from part A. Those are these numbers. All right, A and B. X is the unknown. So, you know that, you know that, you know these two, solve for X. I'll leave you to that algebra. Okay? Usually, again, in class, we've seen two examples of this, but X was given and pH was not. It was the other. But if it could go this way too, where you don't know X, and then, yeah. Remember, the base reacts with the acids, that's why the acid is losing and the other base is gaining. All right, who's next? Yes? What number on page 92? 12. The ethylene glycol. Don't know if it's A or E. Oh, okay, good. I don't even have to do math. Okay, good. We don't even need math because you know it's either A or E for number 12, right?
Yeah, I don't know why it is.
Okay. Anybody? Is it A or E? Okay. Why do you think it's A? Yeah, the concept is it has to go below 0. Because 0 is the freezing point of water. So the answer must be negative. Yeah, if it was positive, again, that would be impossible because that'd be a melting point elevation. Yeah, is that okay? Chen-Yi, are you hanging out or did you want to answer questions too? Huh?
Either one.
Oh, so if anybody, if you're like, oh, I'm tired of this, I want to get the heck out of here, you can, if you have one question, you can ask Chen-Yi. I think he's super nice. He'd probably be willing to answer your question. So if you want to go back there, you can answer your question. If you just want to ask something to get out. Okay, who's next? Yes? Okay, hold up, hold up. Spring 10. So this is page 74. Oh wow, you all are really into colligative properties. That's good. This one right here.
Okay.
Yeah, okay. This is a classic type of problem. Here's how you do it. First, remember the formula. I'll put it over here. Delta T equals IKM. Now, notice all these are aqueous. So K is constant for all of them. It's all Y. So it's the K for Y. K is not going to be a factor for us. The only factors will be I and M. So I'm going to make a little table of I and M. And we're going to multiply those out. And whatever gives us the biggest number will have the lowest freezing point. So I and M. I'll do, well, the easy one is M, it's written right there. Okay, I, for the first one is 2, K and F. Let's skip B for a second. Second one? 2, magnesium and sulfates. Third one, D? Glucose? 1, okay, B is awesome. I forgot about this kind of question. Love it though. It is what? 1, how'd you know that? It's a weak acid. It's not a strong electrolyte. So it does not separate out in solution. Probably less than 5% or so in solution, depending on the molarity. So now I go M times I. 2 times 2 is 4. 0.5 times 1 is 0.5. 1.5 times 2 is 3. 1 times 2 is 2. 2.5 times 1 is 2.5. Looks like A will give us the largest multiple. That means it will have the largest delta T. And thus, it'll have the lowest freezing point. Is that all right? Okay, who's next? Classic problem, by the way. Yes?
What page is this?
This is page 74. Page 74. Who's next? Yes? What? Okay, page 61. Oh, hold up. 61. This one? Okay. All right, in this case, how many milliliters of acetic acid are mixed with that many milliliters of sodium acetate to give a buffer? Okay, so this is back to Henderson-Hasselbalch. We know that literally because it has the word buffer. Okay? So let's write that down. Okay. It tells us in the question, this is 4.2. Let's just go in order here. It doesn't tell me pKa, but it does tell me number 9 that I have acetic acid and sodium acetate. What Ka am I looking for? It's the acetic acid Ka, the one for the acid. So on the back, if you look this up, it's 1.8 times 10 to the minus 5. That's for acetic acid. Cool? Okay. The base and the acid now. Kind of like the previous problem, but a little less crazy. The base, it says there's 13.2 milliliters of the base, and it's 0.2 molar. So I'm going to multiply that stuff out there. And that's going to go up there. The acid, it tells me I don't know the volume, but I know the molarity. It's also 0.2? Yeah. So this is, you can call this whatever your favorite variable is, x, say. So you're going to put this in A, and then your only unknown is x in the whole equation. Is that all right? So solve x. Okay, who's next? Yes? Number 17 on page 70. That's such a good question. Okay. Brings back tears. Okay. All right. How the heck do you do this question? Basically, right? Okay. This is not a reaction you recognize. Okay, it's not your classic like, okay, that makes a lot of sense sort of reaction. But there are pieces of it that kind of look interesting. So whenever they're asking for a K of a reaction you don't recognize, I would start to think, oh, is this actually two reactions added together? If I know those two reactions that are added, I can find the K's on the back of the test and multiply those K's because I'm adding the reactions. You'll see we'll do that right now. Okay. So for this one, I need to write that mess down. Okay, so I kind of recognize, you kind of match likes with likes, so see how this is similar to that, okay? And see that this one is similar to this one. And we're kind of in the acid-base chapter, so I think, why don't I write the general reaction for the acid and the base and see what happens. Okay. So, for the purple one, HF. And I might have to mess around with this a little bit, but let's just see where we get. F minus plus H3O plus. Make sure you will get these general reactions. Now let's do it for the other one. I'll follow suit in brown now. You kind of have two choices really for both of these. You can either write the general reaction for an acid or no, this would be the acid, yeah. Or you could write for the base, you kind of go either way. Are both the reactions in brown okay? They're either the top one's for the acid, the bottom one's for the base. Okay. Now, which one of the brown ones looks like it might fit kind of into this category better? Top or bottom? Bottom, why is that? Yeah, if this one in purple gives the H3O plus, the bottom one down here can help get the OH minus in there. Okay. Now, how do I need to manipulate either of these to add them up to get this overall reaction? I'm going to flip which one? Okay. Multiply by minus 1, is that fair? If I add them up now, will they add up to the top reaction? They do? You cool with that? These two add up to this. No questions? Okay. So now, all I do is look up in the back the K's. So on the, let me find those numbers so you got it. For this one, let's see, I'm running out of colors here. I guess I'll do it in black. KA for this one on the back of the test says 6.6 times 10 to the minus 4. On the back of the test, this is actually a KB reaction, and this is 1.8 times 10 to the minus 5. That's okay, I just looked that up. Now, because I multiplied the reaction, bottom reaction by -1, what do I do to the K? To the 1 over power. I'll raise it to the -1. Now, if I'm adding these reactions, what am I going to do to these K's? To find, let's say, K total. I have to multiply them. So 6.6 times 10 to the -4 times 1.8 times 10 to the -5 to the -1. Is that okay? This is my answer. Whatever that is. So this actually goes in the category of the Hess law type problem for the K's. But I give you a reaction, and I'm making you come up with the consecutive reactions. Because I'm hoping you recognize the acid-base reactions here. Is that kind of all right? Okay, cool.